re-record myself, I guess. Okay. All right, if you just joined us and didn't hear what I just said a few minutes ago, we have a test tomorrow. I'm going to try to get it tonight. I don't know how early, I don't know how much trouble I'll have with it. These things are not really too difficult, but sometimes things don't work. I got something today from administration that said, just fill this out online and submit it. I filled it out, but the submit button doesn't work. So anyway, these things happen. And you have a lot of people right now dealing with electronics who have never dealt with such things in their lives. You guys may have, but a lot of people haven't. And so there's lots of things going on, some of which are comical and some of which are very serious. Yeah. I'm today, I don't know how to put it, kind of sad. I learned about an hour ago that a professor in math died on Monday here on our campus. And I did die on the campus, and I came here in 1967 intending to stay just 9 months. He came at the same time, so I've known him for 54 years. So anyway, that's part of what's in my mind, because it was kind of a shock this morning when I learned about it. Not relevant to the class, but relevant to life, I guess. So fortunately, this was not COVID related. This particular professor is 90 years old, and a couple years older than I am. So, okay. Now, if anybody has any questions about the test that you want to bring up, because I'm going to talk about something else today. Did you see the thing on Blackboard that I kind of talked about yesterday, just kind of hints of things that I tried to put on Blackboard, those little comments of notes of what might be on the test? I hope everybody understands that I'm not saying that anything I forgot will not be on the test. In other words, this was just going through my mind of things I thought you should study, but you're supposed to be able to do anything we talk about, anything we write about, anything that's in the text. Whether or not I emphasize it, it might come up. I don't try to trick you, but I'm just saying, I don't want you to say later, you didn't say that was going to be on the test. Well, you're right, or maybe I didn't. That may have been by design, or maybe because I'm old and forgot. Okay. In any event, you're responsible for everything. And hopefully the test you will find not to be very difficult. I hope. If you want me to make a test to see if you can pass it, I can do that. But I don't see any reason to do that. I know, I believe I can ask you questions you can't answer. So why do it if we know the answer? Okay, no questions from home or abroad? Nobody in here? Okay, well, what we've been talking about for maybe too long is limits and continuity. That involved, I've been trying to stress the epsilons and delta stuff instead of the computations, because I think most of you can take a number, if it's a continuous function, take the formula, stick the number where you're going into the formula and see what the answer is. I don't see that that's a very challenging thing, okay? Sometimes when you stick a number in, you find out that you might get 0 on a denominator or some other problem that does not allow you to get off that easily. You got to do some thinking. Well, sometimes we approach from one side or the other, and we find out that from one side you have a limit, but the other side you don't. Sometimes you have a limit at both places, but they're different. Sometimes one goes to infinity. Sometimes you might have something like sine 1 over x, which doesn't really do anything in terms of approaching one number. Okay, that's what we've been talking about. Okay. And limits is what we use, although continuity is what we like. And yesterday I put some, I put on Blackboard like a little commentary, which I've got right here in my hand for those who can see what I'm doing. That was where we talked about the intermediate value theorem, where I talked just briefly about something called the extreme value theorem. And we also talk about inverse functions being continuous when the function's continuous, okay? The only thing from that set of pages that might be on the test might be a question involving the intermediate value theorem. So I thought, just for a few moments, we might talk about just the fact, if I have a function and you draw a graph of it, the intermediate value theorem, by its name, it's a well-chosen statement. It has to do with if you evaluate the function at one spot and you evaluate the function at another spot, and I'm just picking these kind of at random, but if you evaluate the function at two different places, if the function is continuous on the closed interval between them, so wherever else I'm not interested in, I'm only interested in, for this particular point, between these two places. If you have a continuous function, no breaks in the function and stuff, then any number, and so if we evaluate the thing here and evaluate the thing here, this is the range there. Basically, it's saying every number in between those two numbers, there will be some place on the curve where that number is hit. That's what the intermediate value theorem says, which basically says, if I'm on a hill and you're in a valley, I can't get from one place to the other without going through every altitude in between. And it's intuitively obvious, it's just more difficult to prove mathematically, okay? Now, this is what we do in high school when you have a polynomial and you're looking for a place where the graph crosses the axis. Looking for a root or a zero. The reason it's called a zero is because the y is zero if that happens. It's called a root for other reasons, but I know you know those words, and you spend a good deal of time in high school algebra trying to find such places, okay? It's the intermediate value theorem that tells us because the polynomial is continuous between two places, and if one value is negative and the other's value is positive, that there must be at least one place in between where you have a root or a zero. So, for example, if I have a odd polynomial, an odd one, okay? If you think about an odd polynomial, what does the graph of it roughly look like? We're going to study graphing later, but roughly, an odd polynomial, if you have a positive number and raise that to an odd power, you'll get a very big positive number, presumably. If you take a negative number and raise it to that, you'll get a very big negative number or a very small number, right? One of them is going to be below the axis, the other is going to be above the axis. The intermediate value theorem says someplace in between has got to be a place where you cross the axis. So an odd polynomial always has at least one root. Okay? And it turns out that the intermediate value theorem gives us all kinds of stuff like that that you may not have thought much about, because a lot of times in other classes we do stuff and we say it's not kind of obvious. Of course, you don't question what you're looking for because you think it's obvious. Okay? But the mathematical reason has to do with, in this case, the intermediate value theorem. Okay. Now, we'll later need to know how high the thing gets and how low it gets and some other things about it. That's those other theorems. But continuity on a closed and bounded interval turns out to be a very important concept. And also connectedness, saying that these things aren't two parts or something, turns out to be important in terms of proving things. And so that's why I gave you those pages to look at, a part of it for reference for when we do things later. Okay, and if any of you want to see proofs of these things, I can show you the proofs. But for most of us, it gets into stuff that you probably don't want to study because it takes a month or a couple of weeks. Not that you're not capable of doing it. It's just going down a trail that if we go down there, we won't be going on the trail we're supposed to be going on. It takes us too long to get back. It's not that hard. It's just you have to bring in some other stuff. Okay. So, okay. Any questions about that idea? Because you may have a question about the intermediate value theorem on your test. I may not tell you about it. In other words, I might just ask you some question and you think, well, how in the world am I going to do that? Well, it turns out it's the intermediate value theorem. So on any question on a test for which you have no clue, consider thinking about the intermediate value theorem. That may be the thing you should think about. Okay? Now, other than that, we'll be talking about, I'm going to go over here because I think it's better for you guys at home. We'll be talking about something else. And what you're going to do is, and I don't care where, I'm not talking about zeros anymore. I don't worry about whether this crosses the axis anymore or not. But I want to talk about a graph of a function. And so I'm going to kind of erase part of it here because I don't really care what it's doing. I'm only interested in one place, and that's going to be x naught, so-called. The book likes to use the letter A in the alphabet. I like to use x naught. I like to zero in on things, and a lot of times if I just write x, you don't know if it's moving or staying the same. If I write x sub 0, that means a fixed place. Okay? Now, if I wrote for all x naught, now it's not a fixed place anymore. That's every one. So this is the same as saying that is the same as saying this. We're talking about everything. And so what I call it, suddenly this becomes everything. So when you have x naught, normally we don't have this attached to it because we want to think of zeroing in at one spot. Okay? And the limits are a local behavior. When you're talking about a limit as you go to 1, at that moment, nobody cares what happens to somebody near 5. Okay? The behavior 2 weeks from now is not so important if you're worried about the test tomorrow. Okay? And it's not that the behavior 2 weeks was not important, it's just you zero in on a local idea. And a lot of stuff in calculus is local, okay? Meaning in a neighborhood. And so what we have is a neighborhood, but that usually means a delta or an epsilon, but I'm not going to keep pushing that right now. Anyway, if you look at the graph I wrote here, I drew here, this part of it almost looks like a straight line. Okay? And if I look at bigger area, this doesn't look like a straight line. But if I look real close right in here, this looks, at least from where I'm standing, where you see it from home, you may not see it so well. But from where I'm standing, it looks pretty much like a straight line. And that's really what calculus is about. It's about approximating curves with straight lines. Okay? Now, if we have a function like f of x is absolute x, if I define a function that way, by definition of absolute value, absolute x is x if x is greater than or equal to 0, and it's minus x if x is negative. Now, when people see a letter like x, a lot of time they just think it's positive. What's that? What do you want to do with absolute value? If I say, what's the absolute value of -3, nobody's going to miss that. You're all going to say 3. But how do I get to 3 from -3? I have to put a minus on -3 to get it to be 3. Okay? So, as I say, when people see this, they worry about this minus here. But this minus you put on it if it's negative. And if it's negative and you put a minus on it, it makes it positive. What the absolute value function does is it makes the number positive. What's the graph look like? Well, this is a pretty simple graph. For non-negative numbers, f of x is x, that's called the identity function. That's 45-degree angle. And if x is negative, it's minus x, that's something like this. And so the graph you get for, I hope you can see this at home, but the graph you get I see my cursor is maybe on it. I didn't know I could use a cursor on the graph.
Did you start recording?
I'm sorry?
Did you start recording? Yes, I did.
Oh, I think I am.
Yes, it's on recording on.
Yeah, you are. You're good.
What's your name? No, now you're forever you're going to be on it. Anyway, thank you, by the way. You get this, and it's got a corner. And so a lot of you who've had some calculus before and stuff know the corners in terms of what we'll be talking about are bad, or places where something doesn't exist. Now, what's the something? The word is derivative. Half of calculus is called differential calculus. It involves derivatives. The other half is called integral calculus, which involves integrals, okay, whatever they are. Anyway, what we're going to be talking about for a lot of the rest of the semester is things involving a name derivative or differentiable, okay? And it has to do with behavior locally near something. Now, if you're going down this road, okay, this would be quite an abrupt thing. If your GPS tells you, it may say sharp right turn or something, because they try to tell you this is not going to be something you want to do at speed, okay? And from a mathematical standpoint, a corner is a difficult place, okay? So what we want to do, earlier we talked about continuity, when things are unbroken, so to speak. Now we want to talk about, well, what about corners? What about cusps? For example, what if my graph does this kind of a thing? Now, the way I just drew it, it isn't even a function. But what if you get a church steeple, you get a cusp? That's certainly, at least if you parachute down on it, is not a happy place to land. Okay? So this is a behavior that's worse than a corner. Okay? In a sense, I mean, in terms of smoothness and so forth. But anyway, this is a function which has an abrupt change, and we need to study that kind of problem. Now, if I would turn this over, how do you turn it over? If I put a minus on it, now my new graph is going to look like this. Okay? Upside down, I hope. Could I put a piece of paper on this thing? Now, I'm talking about two dimensions, so you only have a piece of paper, but you understand what I'm saying. Can I balance this with a line? Okay. Is there any one line that approximates that corner? The answer is no. There's lots of lines that might approximate the corner. Okay. In fact, there's two lines that do it real well, but they're two totally different lines. And what we're going to be interested in is when we don't have one line, and we don't have two lines, when we just have one line that approximates the curve. And the original thing I drew over here is this straight line pretty well approximates that curve for a little while. A little while meaning if I go far enough away, it doesn't approximate very well anymore. So it's a local behavior, okay? And that's where epsilons and deltas come in again, because we're always trying to squeeze down and get close to something, okay? Now, so if I start over with my picture, try to draw something here, and let's make it worse. Let's make it something like this. If I take 2 points, take an x0 and I take an x1, okay? Now, my graph looks a little hungover, but anyway, if I take two things, okay, then the point would be x1 f of x1, because I'm evaluating things at a function. This point over here would be x0 f of x0. So I've got 2 points now. They're both fixed and not moving. If I connect the two of them by a straight line, that's called a secant line. Secant line requires 2 points that connect the curve. Now, it's actually a line segment, but I could continue it outside. Okay, so it's either a secant line segment or it's a secant line, depending on how long you want to draw the thing. Okay. Now, there's also something that you have out in life called slope. And the slope that you have, and when people talk about a slope, like I've got a slope in my backyard or something or other, that tells people something about how the vertical is changing with respect to the horizontal. Okay. Now, when you're driving, it might be called a grade instead of a slope. But if somebody says, I live on a steep slope, okay, my house is on a steep slope, that gives you some picture of that, right? And so the slope has to do with how the vertical is changing with respect to the horizontal. So if somebody says we have a 10% grade on the road, okay, and they do this when they warn certain vehicles, usually trucks, because trucks have to worry about stopping more than vehicles. They shouldn't have to worry more, but they warn the trucks, hoping that everybody else is smart enough to realize that the trucks have to slow down, maybe I should too. Anyway, what's a 10% grade? It means for every 10 feet you go horizontally, you go 1 foot up or down. Yes?
Yeah.
Okay. What's the steepest grade you've ever driven on?
45?
45 your car wouldn't do.
Like those
I'm gonna guess the,
The steepest I have been on, I think, is 26%. And that's at 1 and 4. That's pretty steep. Okay. And I had, well, you won't hear about my problems, but I had problems doing it because I didn't have any acceleration in the car. The car was in a problem. And this was in northern Norway. And so, anyway, it's all kinds of problems. There was no help for a week. Well, but you don't want to hear about that because I'm here. Anyway, there's a town in England where people, it's on the coast, and people like to go down to the beach on weekends to swim and stuff. The trouble is there's a 20% grade down to the beach. And so what happens is people drive down to the beach, but they can't get out. So the villagers of the town make lots of money because in the evening, the villagers of the town go out to the road and they push people back up to the, okay? And they make lots of money at this, and it's better than, let's say, police charging for speeding. This is a guaranteed amount of money every weekend because there's like 100 cars that can't get up the road. You charge all these people $10 to get out. The town makes money. Anyway, I won't tell you what town it is, but it's an interesting place because the people are all rich. Okay, secant line, okay? If I get closer to X naught and draw another secant line, okay? First of all, it's shorter, but I'm not worried about the length of it right now. I'm worried about the grade. I'm worried about the difference in the height versus the width and stuff. And so, and now that I've gotten this drawn a little bit, the height is sometimes, now, some of you who had calculus before, I'm going to do something here I don't like. I don't like this notation, but this was the original notation. The amount here between the horizontal and the secant line was called delta y. And it was called a change in y. The delta was meant to be change in y. It's also called an increment. The trouble is that when people developed this stuff, they didn't yet know what real numbers were, and therefore a lot of this is wrong. But intuitively, these guys were geniuses, and intuitively they did it right, but they didn't have the right tools. It's like trying to fix your car with a screwdriver, and that's all you got, okay? They didn't have the right tools, but they were really smart at how they did it. So they got a lot done, but some of it's not correct, but they knew what they wanted. Anyway, the delta x is called the change in x, okay? If I take the fraction between the two, I have what's called the slope, okay? And it's called the slope of the line between these 2 points. Now, you guys know the equation of a line between 2 points. You have to have 1 point and you have to have a slope. I presume you know that already. So you already know about slope, okay? You may or may not know it's connected to calculus, okay? The calculus is all about using this idea of slope. Now, when you get into higher calculus, you'll find out that emphasizing the slope was the wrong idea. We ought to be emphasizing the tangent line, not the slope. Every non-vertical line has a slope, and every slope corresponds to a non-vertical line. And it turns out that what we really ought to do when we go into more dimensions is worry about the tangent thing, tangent line, tangent plane, tangent hyperplane, and not worry about the slope of the line. But we don't know that yet because we're in Calc 1. So we're going to be spending a lot of time talking about the slope. It's going to have other names. It's going to be called the first derivative of the function at the point. And we're going to get to all that. Anyway, basically, if I think about taking smaller and smaller distances from x naught, get closer and closer, and I can't do that very well, very easily in terms of a picture, because as soon as I get pretty close, everything's kind of like a straight line, and so everything's on top of each other, so you don't really see the differences, because the way you've drawn it, when you get small enough, everything's kind of straight. And so what I'm hoping to do is to convince you that, and we're going to do it later with equations and stuff, but I'm hoping to convince you geometrically that as the points get close to x naught, the secant lines start approaching a single line, and it's called a tangent line. Now, that does not happen when you have a corner, okay? And by the way, again, in higher math, we learned the dwelling on corners is also not a good idea. But these are things we'll get to later, okay? So right now we can dwell on this because it's a good example. This particular thing, if I get closer and closer, I still don't get something that's going to behave like the curve, okay? But here it does. And so anyway, if I try to spell this stuff out, what people do, and they do different things, and I'm doing this right now. Right now I'm kind of disobeying something. A lot of times people in elementary classes, the y is always f of x. F of x equals y. I just wrote f of y, and that can screw up half the class, okay? But if I want to take y, I can take y. I'm a teacher, you know, I do what I want to. So if I'm trying to say this, I might be saying, well, see, this already bothers me. So I did x naught here. I think I better put x naught here because I'm approaching a single point. Now the y might be different, but the x naught is fixed, remember? So why am I doing that? Because I want to approach x naught. Now, in what I drew here, I want y to approach x naught. What I'm trying to show you here is the y is a dummy. I could put t here. If I put it here and here, I could put x here. If I put it there and there, I could put s. I could put alpha. I could put Chinese characters. I mean, I could put anything I want, as long as I do it faithfully in the same place. Okay? That's why it's called a dummy. Because it's not really there because you're changing this all the time. You're just talking about the concept. Now, this right here is the slope of a line. What line? Now, I'm going to change some things so that, because if you do what I just did, I'm trying to explain how people can get confused, and I probably just confused you. So most people would not put the y there because that bothers people. So if I put x here instead, they feel better. Okay? Now, what if I ask you to give me the equation of a line through 2 points, or through 1 point with slope? This is called the slope point or point slope equation of a line. Now, because this is a function, what we do is we replace that y naught like this. And so this might be more familiar to you. That's where I'm assuming the y naught is f of x naught. So I can write, and I'm running off the screen here. I can write this as, just changing things to the other side, I can make it look like this. So if I'm given m, this is like high school, and I'm given the point x naught, f of x naught, this is the equation of a line that passes through x naught, f of x naught with slope m. Now, what's slope? It's that vertical versus horizontal. Suppose I'm given 2 points like I was given here. I was given an x1 and an x naught. What's the slope? You have to find the slope from the 2 points. Remember? And what this is, if you're trying to find this, this is the difference in y things over the difference in x things. Now, I haven't written it correctly. But if I have 2 points, x2 and x1 and x1, y1 and x2, y2, if I have 2 points and I make the difference of these things, that's called the slope between the 2 points. I'm just trying to refresh your guys' memory of stuff. Okay? So if I were given 2 points, I find the slope by that way, and if these, now, because I'm given point x naught, I wouldn't use x2 and x1 and x1. I'd probably use x naught and y naught, and maybe x2, y2, whatever. That's if I'm given 2 points. So I'm kind of running all over the place here, but you're used to finding slope, I think. And what's going on here, for any 2 points, if this is x naught and x1, for example, I'm going to have a similar graph here, except this would be between the 2 points. This right here would be y f of x1 minus f of x naught over x1 minus x naught. I know that's not very large for you at home, but it is up here. If I would put x1 and x1 there, this is what you would get. Okay, for a fixed x1, y1. But what we're doing here is we're letting the x approach x naught, so these points are changing. Right. So it turns out that the slope can be defined as the limit of the difference quotient. This thing up here in the box is called a difference quotient. First of all, is it well named? Well, there are differences up there with minuses, and there's a quotient. So it's a pretty well named thing. So if I have 2 points and a function, so I have a function value for each point, the difference quotient is the difference of the f values, the y values, divided by the difference of the x values. Okay. Anyway, this limit, if it exists, has a name. It has various names. The name I like is to call it f prime of x naught. So, for whatever reason, and we're going to have lots of reasons, for whatever reason, what we need to learn about is what I'm now writing down. We need to learn about taking limits of this thing, which is called a difference quotient, and seeing what you get. The name of it, this is called the derivative of f at X naught. We need to know what the function is and we need to know where we're doing it. Now there are other notations that people use. There are good notations and there are bad notations that people use. Again, because the inventors were geniuses, but they didn't really know what numbers were. And so they developed notation to make things work. Unfortunately, some of the notation is misleading, but they were geniuses and they knew when to use it and when not to use it. Unfortunately, some of us aren't all geniuses and therefore we make mistakes because we use the notation at the wrong time. All right. So part of the learning process here is to learn how to use the notation because some of it is not really very good. And we should have gotten rid of it 100 years ago, but we haven't yet. Peter is wanting in. Peter, I don't know how long you've been waiting, if you're in yet. Yeah, Peter, sorry about not being in. So nobody told me to let you in. I apologize. Okay. So, yeah. So this is what we're going to be learning about for the next month or so, is things involving this. All right. Now, there's arithmetic about these things. We're going to turn out that it's going to turn out that if you have two different functions and they both have one of these things, what about the sum of the functions? Do they have one of these things? What about the product of the functions? What about the composite of the function? And so we're going to have arithmetic about learning about these things so we don't always have to compute this limit. The limit involves epsilons and deltas if you don't know what's going on. We try to get away from that as much as we can. But let's take an easy function. Suppose f of x is 3 for all x, for all real numbers. What is the derivative of f at 5 or something? I don't care. Let's let x naught equal 5. So right above here, I have the derivative of the function at x naught. So I want to know what is the derivative of this function at 5? What do you do? And the answer is we take a limit of a difference quotient. And so I take the limit of f of x minus f of 5 over x minus 5 as x goes to 5. This is what I do. So when I get done, I will have, if it exists, I will have f prime of 5. That's what I'm trying to find. So we do it, we stick this in. If f of x is 3 all the time, what do I get? F of x is 3. What's f of 5? 3 over x minus 5. I need to take this limit as x goes to 5. What do you do with limits? You always simplify before you take the limit. What's the inside? I hope it's pretty obvious. It's 0. So what's the limit of 0? 0. So what's f prime of 5? 0. Now, what does, if this means slope, if it does, what slope 0 mean? I mean, you're not going up or down as you go horizontally. It means it's flat. What's the graph of the function f of x equals 3? It is a horizontal line. Now, so part of what we're going to be doing is learning whether or not we believe in this thing. In other words, I just found out that the slope right here is 0. And I'm not off the page, but I'm getting pretty far away. Anyway, the slope is 0 here at this one spot. Okay, if I made a tangent line, it would be y equals 3. Now, what you, I hope, can see is what happens if I change this to 15 instead of 5? I'm going to have 15 down here, but the numerator is still going to be 0. Putting 15 here puts 15 here like this. But remember, you simplify first, still 0. right? And so what we're going to get is a derivative function. In other words, for every x, we have a slope. That makes a function. And we learn the derivative of the function, a constant function, is the zero function. But we do it by doing it point by point. Okay? Then if we have a formula that works for all points, we use that. But we have to do it by doing point by point. Suppose I change the game. Instead of f of x equals 3, what about f of x equals x? Now what's the difference quotient at 5? Do the same. This is the same. This is the same. But f of x is now x. F of 5 is 5. F of x is x. What's x minus 5 over x minus 5? 1. So the limit is, take a limit. It's a limit of 1, which is 1. So now we have the derivative is 1. Does it make any difference if I take different places? Not with the identity function. This is not to be believed this is always true, okay? But for these two functions, it doesn't matter. So what do we say about the identity function? It has a constant slope. Constant slope 1. If I tell you I have a function that has a constant slope, what do you get? You get an idea of a straight line, don't you? Mm-hmm. Constant slope. Slope's not changing. When you get some kind of changing slope, it's when you have some kind of undulating land or something. Okay? Anyway, when we first did the continuities pages, you remember I did the identity function and constant function, I did a square function, and we took some examples, we did epsilons and deltas where we built. Well, what we have to do here is learn how, for different functions, what the derivative is. And for a little while, we've got to actually compute this. And then it's like we did with continuity. Once we compute a few of them, like it's going to turn out that if I have 2x, I'd have to compute that right now. Then you get an answer. And if somebody gives you 3x, you compute that and you get an answer. After you do a number of them, you think, wait a minute, I'm getting the same kind of answer every time. Not the same answer, but the same kind of answer. So then what we do is we change the function to ax, where a can be anything. Because it turns out that we can do this once and find out what this is, and that works for 2x and 3x and 5x. So if I put out a set of notes to you guys, it'll be like the continuity notes, where you start and say, okay, for certain easy functions, what is this thing called a derivative? And where does it exist? So far, everything works. No matter what I put in here, it works. But maybe there's some functions that have some places that don't work. Like, for example, what if I did 1 over x? Now, that function doesn't exist at 0. So is there a derivative at 0? I don't know. Haven't thought about that before. But we're going to find out that if a function has a derivative someplace, it is continuous there. Okay? Now, do you kind of remember roughly from high school what the graph of 1 over x looks like? Looks like this. What happens near 0? You might have this on your test, by the way. As you go 0 this way, the function value gets real big. As you come from the left, the function value gets real small. Yes? So this is going to have an infinite jump. Is this a continuous function at 0? No. Okay, so if I'm correct, if I said if it's differentiable at 0, then it's continuous at 0. If that's true, what's the contrapositive? A test tomorrow. If it's not continuous, then it's not differentiable. And if you look at this graph, it's not continuous. So you could say, if you wanted, without doing a limit, you can say, hey, that's not continuous there. Therefore, it's not differentiable there. If I know if it's differentiable is continuous, that's a theorem we got to prove. So what's going to happen in the future, because I know you've been studying it for this test, in the future, we got to learn what functions have what derivatives and try to develop. We're going to learn the derivative of the sine functions, the cosine function, for example. But we got to prove that. We're going to learn the derivative of the logarithm function is 1 over, but we got to introduce logarithms. And there's all kinds of things we got to learn. Every new function we get, we're going to talk about its derivative now, which is going to involve a limit of a difference quotient or a theorem about that. Okay. And we're going to then also learn about how you put together different functions so that you don't have to do this every time. And that's going to take us a little bit of a while. That's an interesting straight. It'll take us a while. Okay, so once you've taken your test tomorrow, you might start studying chapter 2, because that's where we are going to be. Okay, so I think for a change today, I'm going to stop the